Good day. This is a set of notes that introduces you a wacky world of reaction rates, often called reaction kinetics. Kinetic meaning motion. So when we look at a reaction rate, we want to know how fast a reaction occurs. Is it a fast reaction, is it a slow reaction, or somewhere in between? There is something called collision theory, and it's a pretty easy theory, and it's what we look at in the reaction of magnesium and hydrochloric acid. The premise is that chemical reactions occur because of effective collisions. In other words, particles have to collide, and they have to bump into each other successfully. This may involve geometry, colliding at the right angle, and certainly they have to have enough energy for a change to happen. And the change often involves breaking bonds and forming bonds, and this means dealing with electrons. The more particles that collide effectively, the higher the reaction rate. So we're going to look at the factors that affect the rate of reaction. They're fairly straightforward. Nature reactants we'll come to later. Concentration. Well, you learned about molarity last year, and the more concentrated a solution is, the more particles of a certain chemical you have. And therefore, we would expect 6 molar hydrochloric acid to react faster than 5 molar hydrochloric acid with something like magnesium or zinc. Because we have more particles, we're going to have more collisions, and of those more collisions, more are likely to be effective. Temperature. Well, temperature is a measure of the energy of the particles in terms of their speed. And it turns out if they're moving faster, they're going to have more energy. And if they have more energy, they're more likely to collide successfully. Surface area. Now this factor only applies to heterogeneous reactions. So if you have a gas reacting with a gas, we don't talk about surface area because it's considered to have infinite surface area. But if you had a solid and a liquid, or a solid and a solution, then that would be a heterogeneous reaction, and surface area should affect it. The more surface area, the faster the reaction rate. You simply have more atoms exposed available to react. Now we're going to learn about catalysts in more detail when we talk about potential and kinetic energy. But by definition, a catalyst is a chemical that speeds up a chemical reaction but is not consumed. In other words, you put in this chemical to speed up the reaction, but you get it back at the end. Somewhere along the line, you get it back. So when we catalyze reactions, we actually don't tend to need a lot of catalyst because we do get it back. To measure reaction rate, it's always a function of time. So time is always in the denominator. We need to be able to look at a reaction, and there has to be something macroscopic, something we can see that we can measure. But not only measure, it has to be something that will change. So if we do a chemical reaction, so for example, we put a piece of magnesium into hydrochloric acid, we could time how long it takes for all of that magnesium to disappear, and we could measure it in grams per second. If we did a reaction, say, of sodium carbonate and hydrochloric acid, well, it makes a gas. And so we could collect that gas. And the gas, it makes carbon dioxide. So we could collect it in a test tube that's been filled with water and lying upside down. And all of a sudden the gas would displace the water, and we could measure how rapidly, what volume we produced in a given amount of time. But the other thing we could do is we could actually do our reaction on a scale. And if we make a gas, we could just let the gas escape. And therefore the mass of our system would drop, and we could measure that drop in grams per second. So those are all examples of things that change that we could measure. There are other things, and we'll come into them as we do other questions. Now in this section, we're going to look at reaction mechanisms. And this means for more complicated reactions where we have quite exotic equations, we're going to break it down into smaller, simpler steps and see how they affect the overall reaction. And we're going to learn about catalysts from that and things called intermediates, and we'll learn about a rate determining step. You're also going to be learning about potential energy diagrams, and they're going to look a bit like roller coaster diagrams because you're going to start with reactants and then you're going to climb a hill and you're going to hit a peak. And at the peak of that, that's called the activation energy, where you find the activated complex. And then it's going to spill forward into products. And those PE diagrams give us all kinds of information. And in all likelihood, you're not going to find it too difficult. It may look like mumbo jumbo right now, but once we do some examples, it'll be very straightforward. Well, potential stored energy. So now we look at the energy of motion. We're going to do kinetic energy diagrams. And we're going to look at factors that affect them as well. And again, it may look exotic, but it's really not too bad. So that's our introduction, an overview of what we're going to be doing as we study reaction kinetics. And it's a very quick section, and traditionally it's one that goes very well.